In this lesson, we're going to talk about the area between two curves. So you'll just imagine two functions. I'll put them in red and green here. That's one function. This is another function. If you're finding an area between these two curves, this is one type of problem. You would have to have a starting and ending point because they don't define or enclose a region. So you'd have to say, oh, going from x equals a to x equals b, and then it would find just that little area in there. As opposed to a similar example where you have two curves something like these two curves, where you could be asked, between the functions f and g, find the area enclosed between f and g. All you would do in this case is you would integrate. You can see clearly f is on top, and you'd have to think about that, but figure it out. F of x minus g of x. Because f is on top, it's the one in green. Back here, we'd integrate from a to b because we were told ahead of time to integrate from a to b. And let's say in this case, there's g and there's f. We would integrate g of x minus f of x. So in this first example, you're given the limits of integration from a to b. Whereas in this one, you have to actually think to yourself, well, where is that point of intersection and where is that point of intersection? To do that, off to the side, we have to solve for when f of x is equal to g of x. So use a little bit of algebra, find your points, and then that'll lead you to these two limits of integration. So there's two types of these. Again, one where you're told from where to integrate to where to integrate, and the other kind is where it's kind of your job to figure out what region is enclosed, and then go from there. So let's do an example. We're going to take the region bounded by y equals e to the x, bounded below by y equals x, and on the sides by x equals 0 and x equals 1. So the first thing is, so this whole thing is going to be one of our examples. The first thing is to get an idea of what's going on. E to the x looks kind of like that, right? E to the x has an intercept right there of 1. Y equals x looks kind of like that. And x equals 0 to x equals 1. So let's say that's 1. And there's x equals 0. So effectively, we're looking for that little region right there. So we're going to figure out what function is on top, and of course that's e to the x. And what function is below, and of course that's x. So those two. And then we're told to integrate from 0 to 1 because they bound out the rest of the region. And if you notice in this case, the integration that we're doing involves little slivers that are going up, right? If you could imagine we're taking slice, like little deli meat slicer onto the side of this. It'll give you very thin strips going in this direction. I mention this because in a little bit we're going to also learn how to take strips in the other direction, which is called dy integration, whereas this is dx integration. So now we'll integrate that. So that's the integral of e to the x is e to the x minus x squared over 2, and then evaluate from 0 to 1. So we get e minus 1/2 minus 1 minus 0, of course. So that'll be e minus 3/2. Whatever that is the area. of the enclosed region. Okay. So now we'll do one of the other type, where it is your job to find where they intersect. So we're going to find the region enclosed, the area of the region enclosed by y equals x squared and y equals 2x minus x squared. Okay, so I'm going to approach this abstractly or algebraically first, and then we'll look at a graph for it. So to find the region enclosed by that, the first thing we have to do is set the functions equal and find when they meet. So I'll just send it all over here. 2x squared minus 2x is 0. So I've got my 2 points of intersection, which are at 0 and at 1. Remember, those are x values. So now I know to integrate from 0 to 1. The question now becomes, between 0 and 1, which function is on top? So think about a way that you can determine that. A, of course, you could graph them and see. But option B is that you could pick a value between 0 and 1 and substitute it into these and see which one is bigger. So take a half, for example, and plug it in here. A half squared is a fourth. 2 times a half is 1 minus a fourth. So it looks to me like that function is going to be bigger. Now if you look at them graphically, this is a very rough sketch, but graphically they kind of look like that. And this one, the one that is a downward facing parabola that's concave down, that one is the 2x minus x squared, and you can see from here to here, 2x minus x squared is on top of the x squared graph. So we'll do 2x minus x squared dx, because 2x minus x squared minus x squared. And then you can take it from there. I'm not going to spend the time going through that part. Collect your like terms, do the antiderivative, plug the values in, and you'll have the area right here. Okay, now the other thing is, I know before I went through a brief calculator process by which you can do this. I'm just going to show you that again, but more slowly. For an IB test, of course you're taking the IB test, the paper 2 questions will involve integrals that are much more complicated than this, and potentially they could give you 2 functions that are really hard to find the intersections. So first thing, you would have to have your calculator find the intersection, and then after you've done that, you could then tell your calculator to integrate a function like this. So I'm going to take you through both of those processes. The first one is to put the functions in. So I'm doing that real quick. Maybe you can pause it and do it as well. It is a good thing that you do these, because sometimes if you just watch someone do them, you won't really remember. So I've put them both into my y equals menu, and I'll just graph them just so that we can see them. Now you can see that tiny area in there is what we're looking at. So the first thing I'm going to do now is find the intersections. So second trace, or the calc button, and then you can ask it where they intersect, and make sure you're on your first curve near the intersection. My first curve is the x squared curve. You can see it mousing around there. Now you have to get to the second curve and hit enter. I'm on the second curve, and then I'm not going to bother guessing, but you can see it finds the intersection to be 0, 0. And then from there, If I want to find the next intersection, I can go to second calc again, intersect, which is choice 5, and then mouse over to near the other intersection. I'm on the first curve there, I'm on the second curve there, I'm not going to guess, and of course we find 1, 1. Now, we don't want to have our calculator integrate in this picture because the calculator I'm dealing with is not equipped to do that. So what I'm going to do is I'm going to take this information and incorporate it into one graph, which you can see on the board, that integral up there, 2x minus x squared minus x squared. That's the integral we're about to do. So let me come back out here. So I'm just going to get rid of this top function and bring it down here. And I fully realize that I could just do 2x minus 2x squared, but I'm not going to. Now, if I go to the calc menu, actually, before we do that, let me do the graph, just so you can see what the graph looks like. So the graph looks like that. Now, keep in mind, that graph is not representing either of the other two things. What that graph is doing is apparently from 0 to 1, when we find the integral of that, we'll know the area in that shaded region. So what we're going to do now is go to second calc, and if you scroll down to number 7, which is the integral, the first thing they want from you is a lower limit. And the lower limit for us is 0, so I'm just hitting the 0 key, and then enter. And then the upper limit, I'm hitting the 1 key, and then enter. And you can see it's found our area under the curve to be 1/3. So now if I come back out here and look at the board, if I was to calculate this integral, I'd find it's 1/3. Maybe I'll just do that. That was 2x minus 2x squared, 0 to 1. So that'll be x squared minus x cubed 2/3 x cubed from 0 to 1. So that will be, first of all, the zeros will just go away. So we'll have 1 minus 2/3, which of course is equal to 1/3 again. And remember this graph that I showed you, and I'll just put it up here again. This graph that I showed you neither represents the first function nor represents the second function. That graph is only there to represent the area, that graph is there to represent this function minus this function, which is useful in finding the area enclosed by the two graphs. Yes, so that is that. We're going to, in a I'll just get rid of some of this. Yeah, in a future lesson, what I'm going to do is take you through a similar process, and I just wanted to show you on this picture, again, what I was talking about. In this picture, remember this dx is important because it represents the height, the base of each of these little rectangles that we've built. And we're kind of going through and taking off a slice of those and saying, hey, what's the area of that rectangle and that rectangle and that rectangle? And we defined an integral to be an infinite sum of areas of rectangles. So what we're going to be doing in the future is having functions that are easier to deal with dy integration. In other words, building my rectangles this way and adding up those rectangles, which is fine as well, of course. And so we're going to see an integral blah, 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 dy for a picture like that. We will be getting to that. That is when it's easier sometimes to work with it as a function of y. In other words, x equals stuff with y's in it instead of y equals stuff with x's in it. And that will obviously help you to find areas between curves like that. So we'll tackle that in a future lesson, but hopefully this worked well for you.